Good evening to all. Is the audio and video clear for everyone? So let us begin our today's session on summary of the concept of linear algebra. So in this class I want to discuss some of the previous concepts as well as previous year questions. So if you have any further queries, you can ask with regard to linear algebra. I will give the respective solutions in the Telegram group. In the meanwhile, if you are interested, I want to give one more assignment on this linear algebra concept. And basically, the classes of Monday and Tuesday will be revision of the previous concepts like basis and dimension and linear independence, dependence, etc. Those concepts, because we have some technical issues. So if you are interested, again you can attend those classes and you can ask your queries. So we will have a good time. And from that next day onwards, we will have the new topic, that is solid geometry. We will discuss in the due time, right? So do you want to add anything? Fine. So if you want to say something, you can add. So let us begin our today's session. That so this question was given in 2010. We will discuss that. Suppose the transformation is defined by So I have considered set of all polynomials of degree up to n. So Pn stands for all polynomials of degree up to n. Now the transformation d from Pn to Pn is defined as d stands for the first derivative. It means that whenever I take a polynomial f of x in Pn, then d of f of x is nothing but f dash of x. So that was the transformation what I have taken. Now the question is, if I have considered the transformation d on Pn, what will be its null space? So if you consider its null space, the definition is set of all polynomials in Pn such that d of f of x is equal to 0 in Pn. Because here domain and codomain both are same. So since d stands for derivative, so f dash of x must be equal to 0. That means 0 polynomial in Pn. So from this, what could be the choice of f in the domain Pn? Can you say? Right? So it is nothing but set of all first degree, not first degree, 0 degree polynomials. Nothing but constant polynomials. So whenever you differentiate the constant, the result could be 0. You cannot take the first degree polynomial, right? Because if you take a first degree polynomial, if you differentiate that, can you give the guarantee that the differentiation should be 0? No. That's why we consider only constant polynomials, nothing but polynomials of degree 0. Accepted? All of you? Any questions? Fine. Then we can extend this concept to the operator D as if D is nothing but second derivative. So D of f of x is defined as f double dash of x. So if I consider D in this manner, what could be its null space? So I am saying that I am considering all polynomials in the domain Pn such that whose second derivative is 0. So what is the possibility for domain values? So constant and first degree polynomials. So similarly, you can extend this concept up to kth degree. Let me say I have defined d of f of x is nothing but f power kth derivative. So the null space is nothing but set of all polynomials of degree up to k minus 1. So this is the question asked in 2010. Fine. Is it clear? Right. So let us consider the other one. As we know that generally whenever you consider two-dimensional, three-dimensional vector spaces, let me say r square, r cube, r power 4, etc. For all these vector spaces, we have the standard basis, combinations of ones and zeros. We call it as the standard basis for r cube. Since the dimension of the space is 3, we have a basis consisting of 3 vectors. Symbolically, we write them as E1, E2, E3. In general, E1, E2, E3 indicates the vectors in the standard basis for the real vector spaces. So the suffix value indicates that 1 is in the first position, remaining are zeros. If I have written E2, 2 indicates that 1 is there in the second position and remaining are zeros. This is the actual notation of that. So if you take r power n, since its power is n, we have the standard basis consisting of n vectors. So the first vector E1 is of the form 1, 0, 0, so on 0, n times. Second vector E2 is of the form 0, 1, 0, so on 0, and so on. The last vector En is of the form 0, 0, so on 1. So this is the standard basis for r power n. So are you clear about this? Any doubts? So if we have known this, okay, otherwise please take a note of this about standard basis. So we call them as n tuples. Now based on these, one question is framed. That is, as you know what are E1, E2, so on En. Let us go for a set of vectors obtained from this. I am taking the first vector as e1 minus e2. I will take second vector as e2 minus e3 and so on. Last vector as en minus e1. So if I consider the set of vectors like this, is this set is linearly independent or dependent? That was a question. So please take a note of it. It is also one of the previous year questions. So I am taking the set of vectors as e1 minus e2, e2 minus e3, so on, en minus e1. So in order to verify linear independence, the simple technique is we are going to obtain the matrix and we will calculate the determinant. So based on determinant, if the value is not equal to 0, we say that it is independent. If the value is equals to 0, we say that it is dependent. So can you recollect the method? Say. Are you with me? Right. So let us write these vectors in the form of a matrix first. So e1 minus e2 is nothing but 1, minus 1, 0, 0, so on, 0. Because I am subtracting, I am doing that e1 minus e2. So if you write e2 minus e3, it is nothing but 0, 1, minus 1, 0, so on, 0. The next one will be e3 minus e4, so 0, 0, 1, minus 1, so on, 0. Like this, if you go for the last one, it will be en minus e1, so it is nothing but minus 1, 0, 0, so on, 1, and its previous thing will be 0, 0, so on, 1, minus 1. Accepted? Please check on that. Now, you are going to calculate the determinant by considering any row or column that we know the properties of determinants, how to evaluate them. So on this last row, I am going to apply the operation as Rn tends to Rn plus all the previous rows. I am adding all the rows together to Rn. Now what happens, I will say the last row becomes completely 0. So will you accept? Hence determinant equal to 0. Therefore, these set of vectors are nothing but linearly dependent. So that was the solution for the problem. Fine. Please take a note of it. After noting, please inform. Yes, since it is not a spanning set because it is becoming independent. Please understand, spanning set may be dependent or independent, that we won't bother. If the vectors in the spanning set are independent, then it becomes a basis. So you cannot say that it is not a spanning set. It is a spanning set. Why not? Because whatever the n tuple you take, x1, x2, so on, xn, you will be able to write as a linear combination of these vectors. It is possible to say. Among these vectors, you have one vector which is dependent. That is what we are removing. That's it. Fine. Okay. So can I take the other one, please? I think it was given in 2011. Here I got a set 1 1 1, 2 1 2 and 1 2 3. So this is a set of vectors taken in R cube. The first task of the problem is it Li or not? So I request you to write them in the form of a matrix, calculate the det, and please give me the reply. Is that Li or not? Please go ahead. And give me the determinant value for this 2. What is the det value? So all of you accept that determinant of this one 1 1 1, 2 1 2, 1 2 3 equals to minus 2. All of you accept for it? Right? Then it is a linearly independent set. So you have finished with first part of the problem. Second one is, here he defined a transformation T from R cube to R cube with the condition that T of xyz is equal to x plus 2y plus 3z, x plus 2y plus 5z, 2x plus 4y plus 6z. Right? Now the question asked is, if you substitute the vectors in this transformation, you will get the respective images. Are the images linearly independent or not? If not, give me the reason. That was the question tag. Is it clear? What is to be done? Or you want me to repeat? So I repeat again. So here also we calculate the det, or you can reduce that into echelon form, whatever the procedure that you can do. So if the det is not equal to 0, then it is Li, otherwise LD. If you reduce that into echelon form, if you get a 0 row, it is LD, otherwise Li. Okay? That's it. So let us go for the images first. I think the value could be here as 6, 8, 12. So if you go for the second one, I think it will be 10, 14, 20. And if you go for the third one, 1, 2, 3, I think it will be around 6. So will you confirm this? So please give your confirmation about the images. So do you agree for this? Check for the images. And would you mind please calculate the determinant 2 and tell me, is it independent or dependent? I will wait for your response. Or you can reduce that into echelon form, that also acceptable, by applying suitable row and row operations as per your need. You can divide the rows, you can subtract the rows and reduce it into echelon form. So did anyone has any doubt how these values came? To anyone, you can ask. So after the calculation of that, are you getting a 0 or not? You please tell. Or if you are applying echelon form, are you getting a 0 at the end or not? I think everyone is doing. Is it non-zero? Sure. So all of you say that 20 is determinant of the images, so it is a non-zero set. All right, I leave the part for you. I will give the conclusion. If the determinant is not equal to 0, then it is a linearly independent set. Then there is no need to give the reason. If at all, if the determinant is equals to 0, then the set is LD. Now the question is, why the set has become LD? Now understand that the main objective of the transformation is it transforms one vector into the other. And if you want to transform a basis into another basis, and also a linearly independent set into another linearly independent set, then you must say that the transformation is a bijection. Or you can say that it is invertible. So if you want to say it is invertible, then if you consider n of t, it contains singleton 0. Then only the transformation changes one basis into the other basis. Otherwise, even though if you consider a linearly independent set, the other one may be the set of images. That's all. There is no guarantee that it is going to give another linearly independent set. Okay? Are you clear? Yes or no? I am saying that So T of linearly independent set will give linearly independent set. This is possible only when T is a bijection. If T is not a bijection, then T is just a transformation. So if you give input as linearly independent set, the output is not guaranteed that it is again a linearly independent set. Okay? The thing here is, whenever the function is a bijection and by default it is a transformation, that type of functions we call them as isomorphisms. In other words, they map structure to structure. Otherwise, we can call it as they are structure preserving. So whatever the input you give, similar kind of output will come. The result values will vary, but the result will have same characteristic features. In a simple thing, suppose I have taken a transformation from U to V, and I have taken a set B here, and I mentioned that T is a transformation and a bijection. Then what happens? T of this is equal to, you will get some other thing. Since B is a basis here, B dash is a basis here. That was the phenomena which will be given by T to us. In other words, that is the greatness of T. If T is a bijection as well as a transformation. Such kind of transformations we are calling them as structure preserving functions or isomorphisms. Okay? Are you clear now? Fine. So let us take one more question. I think it was given in 2017 maybe. Generally, whenever a transformation is given, then by default a condition will be given to you. T of xyz is equal to something. And as you know about rank nullity theorem, so from that you know how to calculate rank of the transformation and nullity of the transformation. Now the question is, apart from giving the condition for T, since you know every transformation you can represent it in the form of a matrix by means of a basis. So here we got a matrix for the transformation given by 1 2 3 1, 1 3 5 2, and then 3 8 13 minus 3. I think this question is given in 2017. Now the question is, what is the rank and what is the nullity? Apart from giving the condition for T, the associated matrix of the transformation is given with respect to a basis. The basis is not known, let me say. Is the question tag clear to all? Okay. Now, let me discuss about the nullity of the transformation. If you look at the procedure of nullity of the transformation, whatever the condition is given, that condition we frame it as in the form of a matrix. Let me say, if the condition is given as x plus y minus z, x plus y plus 3z, 4x minus 2y plus z. Then we write them as matrix model, and from this we calculate the null space. That actually we do while calculating null space of the transformation. Since the matrix is given straight away here, there is no need to know about the condition of T. For this transformation, straight away apply row operations, and from that calculate the solution, which is nothing but null space of T. So if you apply the operation R2 tends to R2 minus R1 and R3 tends to R3 minus 3R1, then you are going to get the result as so again applying the operation here, you will get that now please understand that the question is framed from R4 to R cube. Please understand that whenever a matrix is associated with the transformation, codomain dimension is nothing but number of rows, domain dimension is nothing but number of columns. So while solving the system of equations, we take the variables with equal to the number of columns. So if you take the variables as A, B, C, D, this is the corresponding homogeneous system. Fine. So since the rank of the matrix is 2, you will get, as per the formula, number of solutions is equal to number of variables minus rank, that is 2 solutions. So from that, if you take the two values C and D as constants, you are going to get the remaining values. Since you know how to solve the homogeneous system, can I write the solutions straight away? If you allow me, I am going to take C is equal to K1, a constant, and D is equal to K2, another constant. Anybody has any doubts with regard to the solving homogeneous system? Fine. So you are going to get it as so these two vectors are nothing but the basis for the null space. Hence, nullity of the transformation is nothing but 2. And you have to do one more thing about rank of the transformation. Right? So let us go for it. Can I erase this? Please take a note of it. After noting, please notify. Right. So for the calculation of rank of the transformation, we simply do that, take transpose of this one. Why we are taking transpose? Because the transpose matrix will give the images. You can say the images T that you can call upon. So let us reduce that into echelon form. and you are going to get it as applying the operations 113, 012, 024 and 0 minus 3 minus 6. Or 0. So again we apply the row operations on it, and based on this we will calculate the respective solution. That's it. Any doubts for this method to anyone? Say. Otherwise, please take a note of it. I want to take the other models. Can I proceed further? Fine. So it was given in (2010), I think, that I have a transformation T from V to V itself, and T has a special property that T minus T square equals to I. So here I stands for identity transformation, just like I of x equal to x again. Whatever the input you give, the same output will come. I of 5 is equal to 5, just like that. Now the question is, prove that this transformation is invertible. That was the question tag. Okay? Is it clear? Now the thing is, how to prove that it is invertible? Any guesses from anyone? Yes or no? Whenever the condition of T is given to us, using the condition of T, we will determine what could be the possible vectors in the null space. Here the condition of T is not at all given, then how to show that it is invertible? As you know that a function is invertible if it is a bijection. Agreed? Yes. So we will prove that this is a bijection. So we have to prove that it is 1, 1 and also on 2. So what is the criteria for 1, 1? If images are equal, then elements are also equal. That's what we have to prove. So let us take that there are two values in the domain such that T of x is equal to T of y. So if I proved that x is equal to y, then 1, 1 part is complete. Do you agree with me? Say. Now we use this condition. So both sides apply T. again apply minus. So if you say this is 1 and this is 2, one plus 2 gives that. Since t minus t square is nothing but I, which gives that x is equal to y. Therefore, the given function t is 1, 1. Any doubts? Now we have to go for onto part. So if you observe that the function is a operator from v to v itself, that means input and output both will belong to the same set. So let me say for onto, I will take a value in the codomain. So I should find something here so that if I apply t, I should get alpha. Accepted? That is the criteria of onto. Say. So from this part I will say that since I have taken alpha belongs to v, t of alpha also belongs to v. Why? Because t is a mapping from v to v. Domain, codomain both are same. So now what happens? In the domain I got two values, alpha and 2 alpha, t of alpha. Now from this I can say alpha minus t of alpha also belongs to v. Why? Because v is a vector space. So for this part I will apply t. This is nothing but t minus t square of alpha. Therefore, whatever the value alpha you consider in codomain, then alpha minus t of alpha is the preimage, so that t becomes onto. Therefore, it is a bijection, hence it is invertible. Fine. Please take a note of it. After noting, please tell. Any doubts to anyone? Say. If you are clear, I will take the other one. Right. I think it is also given in 2010. So here I got a transformation from r cube to r square, and I have given two bases. And one more thing is given that this was the question tag. It was defined that T is a transformation from R cube to R square, and the matrix of the transformation with respect to the given two bases, say, let me say B1, B2, is this one. Then what is the possible condition of T? That means what is the value of T of XYZ? That was the question. Fine. Is it clear to all what to do? So if you recollect the procedure in finding or obtaining the matrix of a transformation, what are the significance of these values in the matrix? How these were written? It is nothing but the numbers in this matrix are nothing but scalars in the linear combination of the images. Accepted? And the matrix is thus obtained in a way that first column of the matrix is scalars in the first image linear combination. Second column is nothing but scalars in the second image linear combination, like that. And that linear combination is obtained from the codomain basis. So if you want to know the images, it is very simple that if you multiply the column with the basis, you will get the images. So T of 100 value is nothing but 4 into 1 comma 0 plus 0 into 1 comma 1, which gives that 4 comma 0. T of 110 is nothing but 2 into 1 comma 0 plus 1 into 1 comma 1, which is resulting that 3 comma 1. I will repeat that again. Let me say how actually we write matrix of the transformation. The first step is we apply T to a vector. Then you will get an image. For this image, we will write a linear combination. In this linear combination, scalars are written as columns of a matrix. So the first column is nothing but the scalars in the linear combination of the first image. Second column is nothing but the scalars in the linear combination of second image. And third column is nothing but scalars in the linear combination of third image. So if you want to know what are the T images, it is nothing but this one. Clear now how I got them? Now my intention is I want to find a condition of T. Since T is from R cube to R square, if I give a 3D input, I should get a 2D input. How I am doing? So I am making use of these images. So please understand that here the vectors what I am giving as input are nothing but basis. So first of all, I want to write a linear combination. Now I will write the path. You please observe the procedure. So this is the procedure in getting the solution. So please correct me if I go for any computational error. The thing is, I know the domain basis 100, 110, 111. For that, first I considered for a linear combination, because whatever the vector I consider in the domain, I can write a linear combination using the basis. So I get a unique expression for the scalars. So this is the expression for the scalars. So since this is a linear combination, I am going to apply t on both sides. So t of xyz is equal to t of the linear combination. Since t is a transformation, the scalar will come out and we apply t only for the vector. Now as a result, I know the scalar value, I know the image from the matrix given as we computed earlier. Substituting the values and simplifying, this is the required result. So t of xyz is equal to this condition, this is the answer. So you can check for computational errors, but that was the correct procedure. Fine. You can check for that. So you are asking this one. You simply multiply them. So 4x minus 4y, 3y minus 3z, 4z. You add all the first values. This is the first one. You add all the second values. This is the second one. The simplification part I skipped. So actually how it comes? Here 4x minus 4y comma 0 plus there 3y minus 3z comma y minus z, and there 4z comma 3z. Right, if I go wrong you can correct me, no problem. Yeah, that I agree, right. Can you check? While multiplying with y minus z, it will be y minus z, right? You are multiplying both the coordinates with y minus z. So y plus 2z will come. I hope so. So, is the procedure clear to everyone? Please check. Right. So, do you accept for this simplification? What I did? Adding all the first coordinates and adding all the second coordinates. I think mine is correct. I hope so. Right. Now, let us take the other one. So this is also one of the previous year questions. I think it was given in 2005. I got a transformation T from R cube to R cube, and with respect to standard basis, the matrix is so T is a operator, or you can call it transformation, and the matrix of T with respect to standard basis is this one. And the question is given that find the matrix of T with respect to the basis given by one 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 110 011. So it is a little big question, big in the sense it takes a little computation time, but the procedure is very easy and you can solve within 5 minutes. The thing is, I will describe the procedure and step by step answer because we are running out of time. So I will give the description. Whenever you are using the standard basis, means you are using the basic combination 100 010 001. Actually, if you consider the previous question, by taking the first column, multiplying with the basis, we get images, then we need to write a linear combination, and from that we will get the transformation. Actually we do in the regular sense, right? So recollecting the same procedure, since you are using a standard basis, image of the first vector is nothing but 2 1 3. Image of second vector is nothing but 1 2 3. Image of third vector is nothing but -1 2 4. So there is no need to multiply the column scalars with the basis because you are using a standard basis. If you are using any other basis, the column scalars will be multiplied with the basis, then only you will get the image. Since we are using standard basis, the column scalars are nothing but the images. And also, writing linear combination is very easy. Again, you are using a standard basis, because whatever the vector xyz you take, it is nothing but x into 1 0 0 plus y into 0 1 0 plus z into 0 0 1. Please understand that in the previous problem, for the domain basis, I obtained the linear combination. Then for that result, I apply t on both sides. Here, there is no need to do that. It is very simple because we are using a standard basis. And if you substitute the values there, the value of t is nothing but this is the condition of t. Now you can compare the previous problem and the current problem. The difference between obtaining the transformation from a standard basis, obtaining the transformation from different basis. Please check the procedure of previous problem and this problem. Could you agree? In the previous problem, I got a matrix of T, and the matrix is obtained by two different bases, and those bases are not standard bases, they are different bases. So I multiplied the scalars with the basis, I obtained the image, and then for domain basis, I have written the linear combination, obtain the values of ABC in terms of XYZ, then I apply T, and after simplification I got the transformation. Here obtaining transformation is easy because columns are nothing but images, and if you substitute the images, straight away you will get the transformation because the matrix is obtained by means of standard basis. That was the difference. Okay. Are you clear now what I am saying? Any more doubts to anyone? Say. Fine. So if you observe the question tag, we need to find the matrix of the transformation with the basis given in the problem. Usually whenever matrix of T is given, you need to do 4 steps. Linear combination of codomain, apply T for the domain vectors, for the images apply linear combination, and the last step, write scalars as columns. If you do the 4 things, then only you will get the matrix of the transformation. If there is only one basis, the 4 steps are obtained for the single basis only. Now we do the regular procedure for that basis. Usually we do the procedure when the condition is given. So in order to get the condition of T, I deduced the condition from the given matrix. So the importance of matrix here is nothing but I need to get what is T of XYZ. That's why I have used the matrix. So the use of matrix is completed here. So I am erasing this. Now this is my T. Now using this T condition for the given basis, I am applying the T. to get the images. So T of 1, 1, 1, you can correct me if I go wrong for the images part. And before that, I want to write a linear combination for you too. So let us write a linear combination. So I will say, on simplifying, you will get A is equal to x minus y plus z, B is equal to y minus z, and C is equal to y minus x. You can check for that. Exactly. While writing a new matrix, the single basis which is given in the problem will be used for domain and codomain as well. We substitute the vectors in T, we get the images, and we write the linear combination for the same basis. And we use that linear combination for the images too to get the scalars. Clear? Right? Now, I think these are the scalar values, and that could be the linear combination. So, for that linear combination, I am giving number 2. Now I do the procedure. So T of 1, 1, 1 is equal to two and 5 and then 10. Then T of 1, 1, 0 3, 3, 6. If you apply T of 0, 1, 1, 0, 4, 7. So do we accept for these values? Right? Now, for these images, apply combination 2 and give me the scalars. So for the first image 2, 5, 10, I will apply this combination. So please inform the scalars to me. I will write them on board. The first column of the matrix, x minus y plus z, seven minus 5, 3. Am I correct? If I apply the linear combination, x minus y plus z, y minus z, y minus x, if the values are correct. right? So for the second one, six minus 3, 4, and the last one, 3 minus 3, 4. So that was the conclusion. All right, right. Y minus x, 6 minus 3, 0, right? I'll agree with you. That's it. Accepted? So this is a kind of problem you can expect for minimum 20 marks weightage. So there one matrix is given to you with respect to standard basis. Using that, you need to get a condition of T. Later, using the given basis, you need to find a new matrix of T. That is thing. Okay? Are you clear now? So if you are interested, I want to take the other small concept for you. Shall I? Right. So far, one small thing is there. Whenever a mapping is given, for that mapping, we are applying a basis and I am getting a matrix. So actually, if I got two bases, now I am finding a new matrix using these bases. So first what I will do, I will write alpha is equal to a linear combination of the second basis. So now I will get a matrix here. So did you understand how this matrix came? So if you take R cube, the vector space, it may have so many bases. Whatever the basis you consider, the number of vectors are fixed. So if you take the first basis, it contains 3 values only. For second basis, 3 values, third basis, 3 values, and so on. But the values will vary, but the number of values are same. Now, using one basis, I am writing other basis elements as a linear combination. So I am writing alpha, beta, gamma, the elements in the first basis, as a linear combination using second basis. So obviously I will get the scalars. I am writing the scalars as columns of matrix. This matrix, we call it as change of basis matrix or transition matrix. So here I have written B1 using B2. So change of basis with respect to B2 of B1. You can say transition matrix of B1 with respect to B2. Okay? Did you get the logic? Using B2, I have written linear combination. So change of basis matrix of B1 with respect to B2. Similarly, I can write x is equal to so you will get a matrix as so this is change of basis matrix of B2 with respect to B1. What is the interconnectivity here is nothing but these are inverses to each other. So if you know one matrix, there is no need to write the other matrix because the other matrix is inverse of the first one. That's it. So if I say I got a transformation, let me say I got a say I can write these two vectors using this. So this is change of basis matrix of B2 with respect to B1. Now, if you want to write 1, 3 as a linear combination of the second basis, then there is no need to write the linear combination separately. Actually, we write the linear combination and we will solve. But the thing is, if you know the inverse of this matrix, those column values are nothing but the scalars here. That is the interconnection between transition matrices or change of basis matrices. Okay? Are you clear now, all? Tell me. Right. So at this point, I want to conclude our today's session. I think majority of the models which are difficult for you with regard to examination point of view, I have covered them. If you have any other doubts, I will give the relevant material in Telegram. So here we want to conclude about linear algebra. On Monday and Tuesday also, you can ask your doubts with regard to the previous session topics. No problem at all. And we will resume from the next topic, that is solid geometry. So thanks to you all. If you want to say something, you can add. Otherwise, let us close now. The next topic will be solid geometry. Three-dimensional geometry we are going to start. So if anybody has any doubts with regard to syllabus coverage or sessions, etc., you can post your query to the admin directly. So Mondays, Tuesday will be previous classes. So I think Wednesday will be a holiday because it will be Diwali. So from Thursday onwards we will resume solid geometry. So Thursday, Friday, Saturday will be our regular classes. Taking on Saturday. So Thursday will be a orientation class with regard to solid geometry as well as some basic inputs. So from Friday onwards we start the regular things. Fine. Thank you. Any other questions, please? To anyone? Thank you. So it takes 40. So if you are good enough to catch them, then 30 is enough. At the most we take 40. Each topic has equal weightage, 50 marks minimum. I will give the, yes, 30 hours is enough, 30 clock hours. So if you count about linear algebra, so could you tell total how many hours we have taken apart from the sessions we consider? It is around 30 to 40, right? So the same thing for all. But abstract algebra, it takes 50. It is little a dry subject. Slowly we will go fast in that. That's the thing. So thanks to all.